Hi, I'm Darren and welcome to Level Up EE Lab. I've been working on my HF transmitter project and I've made some great progress on the double balanced modulator. Today's episode will catch you up on what I've done and it's going to get into a lot of technical stuff. So let's get started. One quick item before I talk about progress on the balanced modulator. I decided to alter the design of the low-pass filter on the audio board. If you recall, the design cutoff frequency I chose was around 1.1 kHz, and after some further thought and after reviewing some comparable transmitter designs, I decided that frequency was just too low. So I changed capacitor C8 from 10 nano to 2 nano and removed capacitor C9 entirely, which changed the parallel combination with C10 from 20 nano to 10 nano. This new configuration now aligns more closely with the benchmark designs I reviewed. If you've got a copy of EMRFD, the formulas to calculate these response parameters can be found on page 3.24. Here's the before and after results in my updated LT Spice simulation. The response has shifted up in frequency as expected and now has a very slight peak at around 2.8 kHz before rolling off at the same slope as the original configuration. This shift will give me a bit more high end in my voice before eventually getting trimmed in the crystal filter. But that's not the only reason for why I made this change. I also want to make third order intercept measurements on this transmitter, and I need that extra high end bandwidth to allow a test signal to get through the audio stage. Unfortunately, that third order intercept test didn't work out quite like I wanted. More on that later in this episode. Right now, let's get to progress on the balanced modulator. Okay, went straight to the lab here to show off the double balanced modulator. Skipped over the steps where I etched the board, populated the board, tested the board out. That's all fairly routine. I will show some close-up video of the board towards the end of this episode, but wanted to get right into the measurements that I'm doing here. A couple other things. I've got a pretty tight cluster of equipment here on my bench. I don't have room for my microphone, so I'm just using the mic and the camera, so the audio isn't going to be that great. And on top of it all, I got my HP 8657A signal generator, and that cooling fan is running, and it makes a bunch of noise anyway, so the audio is never going to be that great whenever I'm using it. So I'm using this as the RF signal instead of the Arduino, and the reason is I wanted to have as clean of an AC signal going in for these initial tests. And I also wanted some fine control over the power of that signal, the amount of energy that's going in as the carrier. And this guy has fine control. The Arduino does not, so that's why I'm using it. And then the rest of the setup, the Heath 2718 power supply, providing the 12 volt DC. And then off screen, you can't really see much of it, is my 465 scope. And I have a separate camera set up for it. And what I'll do when I'm actually getting some waveforms, I'll just show that video feed on top of what I'm doing so you can see much more clearly what these waveforms look like. What I'm trying to do here is show is the circuit working correctly, and I have the LT Spice simulations, of course, that I did in a prior episode that showed what the expectations were, and that's what I'll be trying to prove out here. And I'll also put on screen right now as a refresher the block diagram of exactly what this double balanced mixer is doing. It's taking two signals. It's taking the audio signal from the audio board and it's mixing it with the carrier signal, and the output is double sideband suppressed carrier. That output then of course goes into the crystal filter, which knocks off one of the sidebands and then amplifies the signal throughout the rest of the IF chain. So that's what I'm going to work today in the lab, is showing how this is working and seeing if it actually meets my expectations. Alright, so I'm going to go ahead and set the signal strength for the carrier signal now. As far as setup goes, the other details, I have my 10 times oscilloscope probe, and the 465 I have set to 5 millivolts on the vertical scale, so it's really reading 50 millivolts per division, and the time base is set to a tenth of a microsecond, I think. So we should see a good sine wave on there. Now as far as the target, again, I want to get to 300 to 500 millivolts peak to peak, so my minimum would be 150 millivolts peak. So that's 3 divisions minimum I want to see here. So let's see, when I turn on the generator, I'm starting out at 0 dBm. I'll get the probe onto the spot on the circuit, and that's definitely not 3 divisions. Let me increase the RF strength. All right, so plus 10 dBm is just barely meeting it. If I go to plus 12, that's pretty good. That's around 350-ish, so I'm well within that range. So I've got my signal ready to go now. And just another comment, this plus 12 dBm I wouldn't read in too much yet, because I've also got a 20 dB pad on this board. I went a little aggressive, not really knowing what I was going to need ultimately from the Arduino, so I can adjust that later. So I would not directly correlate 12 dBm to the power I need from the Arduino and SI5351. Next up is I want to set the audio going into the balance modulator, and I clearly don't have a microphone here. I also don't have my Simpson signal generator. It's malfunctioning and I've had to take it offline for the time being until I can figure out what's going on with it. So instead I've got this little audio board that I whipped up, and I'll talk more about that later, but essentially it's a simple audio signal generator. It has two different frequencies it can generate. I've got it set for just, I think it's around 1800 hertz, 1.8 or just say 2 kilohertz roughly for now. That's going into the actual audio board that I built for this project that I showed in a prior episode, and it's outputting from the audio board into the double balanced modulator. So the target value here in my simulations that I did before, I was targeting 250 millivolts peak or 500 millivolts peak to peak as my maximum signal coming out of my audio amplifier board. So that's what I'm going to do here. I've got two controls. There's a potentiometer to control the amplitude on this signal generator, and then one of course on the audio board. And I've got the oscilloscope probe set at 1x mode now since it's much lower frequency. And I'll switch the camera over here so we can see the 465. Reset it, of course. It's now 1/10 of a volt on vertical axis, and I dialed the time base way down so we can see it. And right now I'm just under 200 millivolts peak, so just a little bit of extra gain should get me there. So I can adjust the signal coming out from the audio signal generator and also the audio amplifier, and crank it up and get it just in between those two divisions. So that's pretty close. That's about 250 millivolts peak. So I've got the audio input all set now. I'm targeting minus 20 dBm as the output from the double balanced mixer, and if you do the calculations into a 50 ohm load, which I've got a 51 ohm resistor here simulating that right now, that works out to about 31.6 millivolts peak, or 64 roughly millivolts peak to peak. So looking at the RF output, what I've done is reconfigured the scope and the probe yet again. I switched it back to ×10 mode. I set the vertical scale to 5 millivolts, and by the way, that is the highest resolution voltage you can get on a 465. It doesn't go any lower than 5 millivolts. And lo and behold, on the screen we can see the characteristic signal of either AM modulation or double sideband. You really can't tell with a scope because if I remember my theory right, the only difference is the phase reversals at each of the zero crossings, and of course you're not going to see that on a scope. But most importantly, we can see what that peak voltage is. And going back to my design specs for this, I was trying to hit minus 20 dBm coming out of the balance modulator. That works out to 31.6 millivolts peak going into a 50 ohm load, and you can see with each division here about 50 millivolts. That's awfully close, if not a little bit more than 30 millivolts. So that means it looks like everything's working fine. And just one last little interesting thing, if you set the time base even higher on the scope, you can actually see the baseband frequency there. That's the 5.5 megahertz RF signal, and it's being modulated at 2 kilohertz by the double balance modulator. I do have one more measurement I want to do here on this balance modulator, and that's a more direct measurement of the output power. And what I've got here is a device I've shown a few times, I think, on some of my other projects. It's a home-built power meter. It's based on a very common integrated circuit. It's Analog Devices AD8307, and you can find plenty of examples online of how to use that IC. It's a logarithmic amplifier to measure quite accurately RF power. In this case, the one I built, it's got a 70 dB range from minus 60 dBm up to plus 10 dBm. The design comes from a QST article, June 2001 issue, I believe it was. You can also find the design in the EMRFD book on page 7.7. And very simple, it's internally powered by a 9-volt battery.
I've got both analog output. I've got a meter here that I used for peaking circuits or when I'm tuning something and trying to find peak power. And then I've also got a feed-through capacitor here that I can hook up to a DMM like this one here and actually get a more accurate reading. And of course, power input goes right here. So I've reconfigured the coax connection here just to go directly to the meter. It's got its own 50 ohm load on the inside. So I'll hook up the DMM to the feed-through cap. Of course, I've got to turn the meter on, and there's going to be some base reading in there. That's just noise. You know, clearly I don't have this well shielded. In fact, it's not shielded at all around this area, so I'm going to be picking up some noise. But for the magnitude of the reading I'm making, the noise really doesn't matter. So then the next thing I do, I'll turn on the RF signal and see what reading we get. So the needle went up. I'm getting 4.034 volts output, and the way this meter works is it's just a linear function from voltage to scale it to dBm power. And I'll show on screen the Excel spreadsheet that I've been using over the years just to plug these values in. I've got several different calibration curves depending upon frequency because it does roll off a little bit as it goes higher in frequency. So the one I'm using is for 10 megahertz, and that's pretty close, actually close enough. So I just take the reading there, it was 4.034 volts, multiply that by 16.1, and then subtract 85.7 minus 20.8 dBm. So very good. That's confirming through another measurement that I've got the output power that I wanted from this double balance mixer.
Earlier I mentioned a little bit about the audio board, and I want to talk about that now. What this is, it's another little project that I whipped up from EMRFD. It's on page 7.14. It's built up with a bunch of op amps and discrete parts. Pretty easy construction. In fact, I already had all the bits and pieces in my junk box, including a little wireless, or solderless, I should say, solderless breadboard. Whipped it up, and I was in business. And the key features of it are, it's got two tones. One you could switch on and off, and the two tones are not harmonically related to each other, so it's good to use this to drive a transmitter or other audio circuit where you're looking for intermodulation. The highest frequency tone, the way I got this built, is 1.89 kilohertz, and the low frequency tone that I can inject by switching on and off a little switch there is 803 hertz, 803 hertz. It's a little bit off the design centers, but that's fine. It's just the way the component R's and C's matched up. And the other nice thing about this circuit is the two tones are equivalent power. One's not significantly stronger than the other. That's another thing that you would need for IMD measurements. Now, I was a bit naive. I was thinking, I'll just set this up and drive it into my spectrum analyzer and I'll be able to look at the third order intercept. Well, I overlooked a small but mighty detail with my spectrum analyzer. You really need a super fine resolution bandwidth on the order of 100 hertz. And my home-built spectrum analyzer, its tightest filter is only 30 kilohertz. So, that is not going to work. But I thought about this some more, and what I can do to at least get a qualitative measure of the performance of the stages so far is use an SDR. In my case, I've got an AirSpy HF Plus, and I've hooked it up directly to the output of the double balance modulator with a step attenuator in between them. The output of this guy, of course, minus 20 dBm, and the AirSpy will handle up to plus 10 dBm, but I didn't want to push it that far, so I put in a step attenuator so I can dial it down about 20 dB or so. And then I'm just using plain old SDR console to look at, again, qualitatively the signal that's coming through all this chain. And I think it's pretty interesting that what we can see even with just this limited qualitative view. So let me switch over now and let's take a look at it in the software. All right, I've got the SDR console configured. I've got the center frequency at 5.5 meg. Of course, that's the carrier frequency for this little rig. I've got lower sideband and upper sideband configured with a 3.6 kilohertz filter just to keep it pretty wide. And I set the vertical scale just to try to fit all of the display within this window. Again, I'm not going to try to quantify what we're seeing here. So let me turn on the RF. And bingo. We're listening to that lower sideband signal at 1890 hertz, 1.89 kilohertz coming through. You can see it over here on the IF display. You can also listen to it on upper sideband, and there's a very slight shift in frequency there, and that's to be expected because my signal generator frequency doesn't perfectly match 5.5 megahertz exactly the same as the AirSpy HF thinks it is, but nonetheless, We got lower sideband, upper sideband, exactly as expected from a double balanced mixer. And of course, there's no strong carrier. There's some artifacts here. I'm not sure we can trust that to say that that's carrier bleed through or not. And also this other garbage around each signal. I wouldn't read too much into that. And the other observation we can make, though, is that's the second harmonic, that's the third harmonic, that's the fourth kind of off screen, and then the fifth of the audio input. So that's showing up coming through. But again, that's going to get knocked out, of course, because my crystal filter is only going to take what's in this region right here. Now, I can go ahead and turn on that second signal at 803 hertz. And we see it there, and we hear it mixing in. And remember I said earlier that those signals were equivalent strength, and they still pretty much are going through all the stages here. So that's good. Now, the real gem to try to pick out of this would be, well, what's the third order intercept? And again, this is not a spectrum analyzer. This is a spectrum viewer, and I don't want to read too much into it, because if it was a true spectrum analyzer, we'd be able to find that third order modulation a signal coming through, and none of these are them. What I've done, I played around with this for about an hour or so and changed the magnitude of the signal strength going into the stage, and I could get these 4 peaks to go up and down, but none of these were moving at 3 times the rate, which is a requirement for that third order intercept. So it's really not picking it up. It's not showing it anywhere on there. But no worries. This is showing at least qualitatively that the stages are working the way that I want. And then when I put in that next stage with the crystal filter and the IF amplifier, we'll be taking only this portion of it. And of course, there's one more thing I can do with this setup while I've got the hardware on my bench. I can swap out that audio generator for a microphone and see and hear what my voice sounds like. Let's give that a try. Alright, this is what my voice sounds like coming through my PG48 mic into the audio board and into the double balance modulator. Pretty decent. Now, a few observations. Of course, I can switch over to lower sideband and hear the exact same signal. I'm going to be using the crystal filter to knock out this sideband and only keep the upper sideband. And then, of course, this signal is pretty weak. It's only minus 20 dBm with a constant tone. So, in theory, even though I could put this on the air right now and communicate, it's just way too weak. And, of course, there's all this extra spectrum garbage here that would create all kinds of interference. So, don't want to have that out on the air. And that's what that filter will help do. And then, of course, the IF amp and the rest of those stages, including the second mixer, are going to boost it to the final transmitted frequency. And just one last little thing to play with here, of course, just like anybody that's familiar with communicating in sideband, if you start getting off frequency, the voice starts to get really distorted, and of course you get it's either some carrier bleed through or just some 60 hertz hum that's being picked up that we're hearing in the signal there. But yeah, if you're right on frequency, you're going to sound good. If you're a little bit off, you're going to get some pitch shift there. So all in all, I'm pleased with how this is working. So there you have it. That's progress on that double balance modulator. Now, a couple quick comments here before I close. I did use the term modulator and mixer kind of interchangeably in this episode. And if you really want to get technical, a modulator is a mixer, but not every mixer is a modulator. So probably should have said modulator throughout the whole episode, but I think you guys understood what I was talking about. I did promise to talk a bit more about the board construction, so let's take a closer look at it now. I'll do a magnified view so we can look at it. So looking at it close up, most of the components, of course, are surface mount, including a couple of tantalum caps. I had 2 at the right value that I just put on there rather than use leaded electrolytics. But speaking of electrolytics, on the other side, there's 2 electrolytics there, the trimmer pot for the carrier balance, and then there's that little tricky transformer I had to wind. It's got a bifilar primary and then a simple secondary, so getting all that stuff crammed in through that small FT3743 core was a bit tricky. And here's that 2-tone audio board that I mentioned. It is a bit cruder than the double balance modulator. As I mentioned, I just used a piece of perf board, scrounged around in the junk box, and whipped this up in just a few hours. The construction is pretty simple. There's 3 op amps there. They're MC1458s, and 2 of them are doing the oscillating, 2 of them are buffers, and then the last 2 are combining the signals and also buffering the output. So pretty straightforward. And like I said, you can find the schematic for this in EMRFD.
That's it for today's episode. I hope you enjoyed this little walkthrough and demo that I did on the double balance modulator. Looking ahead, of course, the next item in the transmitter chain is the IF amplifier and crystal bandpass filter, followed by the second mixer, which of course is going to change the frequency to the actual transmitted frequency. So look for that content in the future episodes. As always, thanks very much for watching this episode. I hope you did enjoy it and you know the request. Any questions or comments, you know where to put them in the box below. So until next time, bye for now.